So today we're going to be talking about rare earth elements, and the rare earth elements on the periodic table are primarily located in that grouping of metals at the bottom which don't fit conveniently into the periodic table. This is called the lanthanide series of elements, and then we also, in addition, have selenium, yttrium, and lanthanum, 21, 39, and 57 for atomic units, sort of thing. So the one thing about the rare earth elements is they're not actually very rare. So if we look at the abundance of elements in the Earth's crust, the most common elements in the Earth's crust are aluminum, silicon, iron, titanium, calcium, those sorts of things that make up soil. But when it comes to metals, very common metals like copper are found in abundance in the Earth's crust of about 68 parts per million. And then everything on this list that is in bold and in a gray box is considered to be a rare earth element. And so, for example, cerium and lanthanum are the two most abundant rare earth elements, and they're more abundant than lead, but not quite as abundant as copper. And then you go down the list and you think of something that's really rare like gold, at 0.0031 parts per million. That's a factor of 100 less common than thulium and lutetium. So these rare earth elements are not actually that rare. It's a misnomer that came about from a naming convention that happened kind of in the 1930s and 1940s. And it was named that way because these rare earth metals do not occur in their elemental form in nature. They only occur inside minerals for the most part. And so you have to work to extract them from those minerals, usually converting them to metal oxides, and then later on, stripping off the oxygens to get to the pure metals through a multi-step process. So the rare earth elements can be divided up into three groups: the light rare earth metals, the medium weight, and the heavy weights. And all of these rare earth metals have industrial applications. And some of these are served in magnets, some of these are in catalysts, some of these are in phosphors, and some of these are used in lasers. But this isn't the most convenient way to look at the usefulness of these rare earth elements. So we'll look at this in a different way. Let's take a look at some of the materials that are needed for renewable energies. So if we take a look at solar cells and the construction of photovoltaic films, you'll see that there are several elements that are not considered rare earths which are used in those: indium, gallium, tellurium. If you start looking at the rare earths, they make their appearance in the use of magnets and the use of batteries. And the neodymium magnets are some of the strongest and most lightweight magnets that are actually on the market today. And they're used for power generation inside the wind turbines, and they're used inside vehicles. And then we also have uses for rare earths in specialized batteries as well that are being used in vehicles. The primary metals that are being used for those batteries are lithium and cobalt. Lithium happens to be the lightest metal, and it's able to carry quite an electrical charge without much weight, which has a good application in vehicles such as cars and airplanes. And then lastly, you'll see that a lot of the rare earths are used in lighting. Now, specifically, they're used to generate light within light-emitting diodes, so the LEDs. So some of these will generate red light, some of these will generate green, some will generate blue. And by putting those together, you can actually create the spectrum of colors that you need on a computer screen or a television screen or your phone screen. Another way to look at this is the type of metals that are used in individual applications. We've already looked at wind turbines. which use neodymium and dysprosium and promethium. And then, we have cordless power tools, which use batteries. We've got earphones and speakers, which use, in addition to neodymium and promethium, use gadolinium. We've got energy efficient light bulbs. We have LCDs and plasma screens. We've got hybrid vehicles, catalytic converters, rechargeable batteries, and a lot of use in the smartphones for the screens. So a lot of good uses for the rare earth elements. If we look at the amount of rare earth elements being used for these different applications, the number one application is for magnets, followed by catalyst, followed by polishing and batteries. And then some of this is also used in ceramics and for phosphors for lighting. So let's take a look at the catalyst. Recall that an automotive catalyst, what they're doing is they're trying to scrub out the nitrogen oxides from the tailpipe before it makes it to the atmosphere. And they use platinum for that, but they also use the following rare earth elements: cerium, lanthanum, neodymium, and promethium. And primarily they're using 60% cerium oxide, or 90% cerium oxide, in order to serve as a catalyst. But that's not the only way that catalysts can be used. They also use a catalyst in the oil refining process. It allows them to crack some of those long chain hydrocarbons and increases the per barrel yield of gasoline and diesel by about 7 to 10%. And primarily they're using lanthanum at 90%. Magnets, these rare earth magnets are stronger per unit weight and volume than any other magnet type, and they're used basically anytime you need a small, strong magnet that is lightweight. So this can be in computer hardware, it can be in hybrid vehicles, it can be in airplanes, and neodymium is the metal of choice for that. We can also alloy these rare earths into other metals for other specific purposes. So example, we have the nickel metal hydrate batteries, uses lanthanum and a nickel anode to protect against corrosion. And the Prius vehicle battery pack uses between 10 and 15 kilograms of lanthanum in its batteries. There's also possible to use some of these metals in alloying special steels, cerium being the most common used for that purpose. Polishing. Cerium oxide, cerium powders are really good at giving a very high gloss polish. It's used in all lenses. It's used in the generation of screens, mirrors, and even polishing gems. The glass in your camera and the glass in your smartphone is made up of about 50% lanthanum. And then the cerium is also added to the optical glasses to basically prevent the UV transmission. And then we have the phosphors. We have yttrium, europium, and tiberium, which are the red, green, and blue phosphors used in lots of different types of light bulbs and LEDs. And then they're also used in ceramic capacitors, and other ceramics can be stabilized for use in solid oxide fuel cells. So the common ones here are yttrium, lanthanum, cerium, neodymium, and promethium. So how do we get these rare earths from the ground to our products that we use every day? Well, it's a multi-step process. And the first part is starting, of course, with exploration. The rare earths, as I said before, are not that rare, but you do need to find places where they're concentrated above the global average in order to make the mine efficient and cost-effective. And there are a couple of places in the United States where you have ore deposits for rare earths that are enriched in those rare earths. One place is in Southern California, but there's actually some other places in Idaho that have enriched rare earths. So the first thing you have to do is you have to mine them, and then you have to separate out the rare earth minerals. So you're essentially concentrating the rare earth minerals then you can send those off for separation and processing, where they further take those rare earth minerals and break them down and turn them into metal oxides. And then once you have the metal oxides, then you can further refine them into metals and alloys that can be directly used in the manufacturing process for magnets and electronics and glass and that sort of thing. And so we refer to the mining and the concentration as the upstream supply chain. The midstream is the separation and processing, making a useful metal out of the concentrate. And then we have the downstream, which is actually taking that metal and turning it into useful products through the process of manufacturing. So, how do we mine these rare earths from the ground? Well, it depends upon the ore body that you're going after. If it's near the surface and relatively well distributed, then you can do an open pit mine. If it happens to be further below or associated with veins, then you need to go underground. And both of these types of mines are used in mining rare earth just like they are for precious metals. So mineral processing is a huge component of the concentration. So we start off with the ore body itself, and then we have to basically separate out the rare earth minerals from the other minerals. And generally speaking, these rare earth ores are anywhere from 9 to 13% of the ore is rare earth. And so you have to strip away the other essentially 90% of the material away as waste. And then once you have that concentrate, which is made up of the rare earth minerals, generally speaking, about 50% of that is going to be cerium, and another 30% is going to be lanthanum, and another 10 to 15% is going to be neodymium, and then you have a slight sliver of other rare earths, which are less common. And then you have to figure out a way to actually separate the individual rare earth elements from one another. One way that is done is through the use of flotation. So they will take the concentrate and the separated rare earth minerals, and they will put those into tanks and mix them with special chemicals that will further break the bonds associated with the minerals. And they'll add in some flocculants and some aeration so that they can then start to create bubbles. And the metals themselves will end up attaching themselves to these bubbles and floating to the surface. And then you can skim off the top of all of this froth, and it'll be heavily enriched in those rare earth metals. Then once you have those rare earth metals, then you have to separate out the individual sort of thing. And they typically do that with solvent extraction, using very small differences in the solubility between the individual rare earth elements. And they often do this at low pH and mixing with organic chemicals. And it actually generates quite a bit of toxic waste associated with this that then has to be dealt with to prevent it from getting into the environment. So to summarize, the rare earths are not rare. There are lots of places around the world where you can mine and concentrate the ore. The problem is that taking that concentrate and turning it into the metal oxides and later the metals and then the products themselves, that's the midstream and the downstream part of the supply chain. And the midstream and the downstream supply chain are dominated by China. They have 6 state-owned rare earth companies that operate 30+ refineries, and they're doing almost all of the refining of these metals for the entire world. So where are the mines where they're actually extracting the rare earth metals from the ground? So in North America, we have the Mountain Pass mine in California. South America, we have one in Brazil. Then we have several in Asia and one in Northern Europe. If we look at the rare earth oxide production, so it started off that it was done worldwide, and then in the United States, the Mountain Pass mine came online in the mid-1960s and was generating a lot of the world's rare earths for many years. And then China decided that they wanted to take over the rare earth oxide market. And so they started production in the mid-1980s and quickly ramped up and were able to do this in a much cheaper way because they didn't have the same environmental regulations as in the United States or in other countries. And they basically drove the other countries out of the business and have a near monopoly on rare earth oxides around the world. So how do they do that? Well, they basically are the only country that has significant capability to do the midstream and downstream part of the supply chain. So they mine 70% of the rare earth elements in the world, and 30% are mined outside of China. But because the places outside of China don't have the facilities to be able to process the ore, a lot of that ore is sent to China. So that although China only mines 70% of the rare earth elements, they do generate 85% of the oxides. So half of the world's mines outside of China are sending their material to China for processing. And China ends up creating 90% of the rare earth metals, 90% of the alloys, and 90% of the magnets. And you can see that dramatically here. When we look at the world production by country of these products, China by far is the world dominant in producing these products. So let's take a look at what the U.S. imports versus what the U.S. develops domestically. So here we have the net import reliance. So for example, arsenic, we import 100% of the arsenic that we use in this country. We import it from China, Morocco, and Belgium. And so everything on this list right here, we import more than 75%. So these are primarily things that we're importing from other countries. And if you'll notice that about 10 or 12 down, it says rare earths. And the rare earths, we are currently importing 100% of that. And of course, that's coming from China, Estonia, Japan, and Malaysia, but China has the bulk of the market, so I'm assuming we get about 90% of our rare earths from China or greater. So what is the United States good at producing? So if we look at the bottom of the list here, so these are things that are primarily produced domestically. We have aluminum, iron, and steel. So why are we good at aluminum? Well, because we have ore bodies, but more importantly, we have cheap electricity in the form of hydropower in the Pacific Northwest. And they use that cheap electricity in order to refine the aluminum. It's an extremely energy intensive process, and that's why they really encourage you to recycle your aluminum cans, because it's actually a lot cheaper to recycle than it is to get the aluminum from the ore itself. We also can generate a lot of iron and steel from the upper Midwest, where we have lots of iron ore, lots of coal, and to be able to create steel. But you'll notice the little bit further up, copper, 35% of the copper is actually imported into the United States, and so domestically we are producing 65% of the copper that we use. So if we take a look at what it would take in order to convert our fleet of vehicles to 100% electric vehicles, it's going to require significant investment in the construction of batteries, and that's going to require more metals. So if we were to completely convert our our vehicles to electric, it would cause us to have an increase in the lithium production by 3,000% and cobalt by 2,000% and the rare earth elements by 655% in order to meet the need of the world. So this is a growth market that is currently being controlled by a monopoly of China. So if you think about this from a national security perspective, then you can start to analyze whether or not there's a risk associated with these being reliant upon these rare earth metals. So on this axis, on the x-axis, we have the supply risk, and on the y-axis, we have the importance to clean energy. So that would be electric vehicles. And you can see that in the 0 to 5 year time frame, the U.S. government thinks that there are about 6 elements that have a critical bottleneck in the supply, and that's dysprosium, neodymium, terbium, yttrium, europium, and indium. And then, of course, the United States is looking out further from 5 to 15 years. And you'll still see 1, 2, 3, 4, 5 of these are still considered to be high risk for supply disruptions: neodymium, dysprosium, terbium, europium, and yttrium. And you'll also notice that lithium has now moved into a near critical sort of thing because of the use in electric vehicles and batteries. So let's say that we wanted to, for national security reasons, develop our own mining and refining processes. Well, it takes time. So for example, since the year 2000, there have been 14 major metal mines that started production. And generally speaking, it took on average about 10 years with a range from 6 years to 23 years to get these mines up and operating. And that's just the mines themselves. If we wanted to create the refining of the metal oxides, of the rare earth elements to get them to metal oxides and later metals, we'd have to start from scratch. And right now we do not have that capability. It's something that we would have to develop. Canada is currently trying to develop its own supply chain capabilities. But the problem that they're running into is that the environmental regulations make the process expensive to do in North America compared to China. And so there's a Canadian company that is lobbying for government subsidies in order to, or waiving environmental regulations in order to be able to meet the goal of becoming self-sufficient in terms of the production of rare earth metals and products. So what are the potential environmental impacts associated with this? Well, the ore itself often has other types of metals in it, and a lot of those metals are actually radioactive. So for example, these rare earth elements are often co-located with thorium and uranium. And so when you extract the rare earth element minerals and leave behind the tailings pile, you're basically concentrating the thorium and the uranium in the tailings pile, and that has to be dealt with at as a toxic product. And then, the waste generated through the process of breaking apart the rare earth minerals and trying to extract the metal oxides, that entire process generates a lot of waste and a lot of toxic waste because a lot of that is done at very low pH with a lot of organic compounds involved. And so you have potential issues associated with that as well.